Welcome to The Explainer. Today, we're diving headfirst into a genuinely fascinating source text by Dr. Guy Lakeman, and it outlines nothing short of a total paradigm shift in computing. We are looking at a profound transformation in how artificial intelligence actually operates. We're talking about moving from a system that generates just massive amounts of heat to one that uses the power of light itself. It's a super compelling look at how we might just solve the looming energy crisis caused by our endless digital demands, making sure your everyday AI tools don't eventually just melt down the entire power grid.
Okay, let's dive into this. Just look at this stark contrast. On the left side, you've got a modern, advanced AI silicon chip, and it pulls roughly 1,000 watts of power. But on the right, the human brain, the absolute most complex intelligent system we know of, and it runs on about 30 watts. That is basically a fraction of a light bulb. That massive gap in energy efficiency is the core problem our current technology faces today, and it's exactly what this incredible new wave of innovation aims to solve.
Because the source text frames a massive infrastructural and environmental conflict. As AI models grow from standard large language models into these insanely complex mixtures of experts, they're demanding more and more massive intelligence warehouses. So what actually happens when that thirst for computational power starts melting the grid? We're currently facing a reality where just supporting basic AI infrastructure is going to demand unprecedented, uninterrupted megawatts of power. Dr. Lakeman outlines a pretty grim warning here about what he calls the silicon bottleneck. See, traditional computing relies on moving electrons around, and doing that generates it generates a ton of friction and heat. Because of this, modern data centers aren't just servers anymore. They require massive industrial cooling systems just to pump all that heat out into the atmosphere. The text even notes that these overheated hothouses are actually beginning to disturb local weather patterns around major cities. We're quite literally hitting the physical limits of what traditional silicon scaling can handle without causing a full-blown environmental disaster.
Section 1. Enter photonic processing, computing with light. So this is a massive pivot from the heavy friction of electricity to the frictionless freedom of light. At its core, photonic processors are microchips that use light particles, photons, instead of electrical current to process and move data. And the absolute most astonishing parts? Because they use light, they generate essentially zero heat at the point of computation. It's wild. And the author makes it very clear, this isn't some far-off science fiction fantasy. It is a reality that is filtering into development right now. Now, what's really interesting about this slide is the glowing blue fiber optics feeding directly into the chip. Instead of traditional copper wiring that causes all that electrical resistance we just talked about, photons glide right through these microscopic etched tracks called waveguides. They face practically zero resistance, which means zero heat, and quite frankly, unbelievable speed.
Let's break down the dense science of how this actually computes, because it's super cool. First, as we just saw, photons travel through waveguides. But here is where it gets crazy. Through a process called wavelength division multiplexing, different colors of light can share the exact same physical space simultaneously. Imagine a highway where different colored cars just safely drive right through one another without crashing. And the math? It's completely analog. Mathematical operations happen instantly through the natural interference patterns of light waves, totally bypassing the need for sequential, step-by-step binary transistor switches.
The performance metrics detailed in the source are just astonishing. These chips run at roughly 30 watts, bringing us right back to that incredible human brain efficiency we started with. In evaluations against standard GPUs, they boast a 50-fold advantage in matrix vector multiplication. 50 times! Even wilder, because this hardware does math via physics rather than transistor logic, it calculates complex nonlinear functions like sine, cosine, and Fourier transforms natively, basically in one shot. Think about that for a second. In one test, a photonic processor running at a mere 200 megahertz achieved better image reconstruction results than a traditional CPU running at 2.4 gigahertz. It's literally doing better math at a fraction of the clock speed.
Section 2. Holographic memory, rebuilding how we store data.
So, the crucial point is how we physically store all this information, because incredibly fast processing is only half the battle. Multidimensional holographic data storage uses laser light to record overlapping data patterns. Instead of storing data on a flat, two-dimensional electronic surface like we're used to, this technique combines amplitude, phase, and polarization to embed data throughout the actual three-dimensional volume of a material. Think of it like moving from writing on a flat piece of paper to suddenly being able to write inside a massive 3D crystal. It just massively expands storage capacity and shrinks the overall footprint of our data centers.
And the memory innovation doesn't stop with just light. The text also highlights advanced non-traditional scaling, like the GI or return to one single electron memory design, using graphene. You can see the massive leap illustrated here. We're talking about moving from requiring 200,000 electrons down to confining just one single electron to maximize stability and density. That completely bypasses traditional lithography scaling limits.
Section 3. The Global Photonics Race. A shifting geopolitical landscape. Obviously, this technological leap isn't happening in a vacuum. Dr. Lakeman uses some very striking language here. He argues strongly that while North Atlantic nations are bogged down in the heat and power problems of silicon, the East, which he refers to as the lands of the rising sun, is pioneering this light-based salvation. It's important to note, the author is highly critical of the North Atlantic's current approaches, arguing that Western nations are suffering from energy waste and supply chain disruptions, while Eastern nations are rapidly innovating. And this brilliantly illustrates the data he uses to back up those claims. As this breakdown of global mass production shows, China currently holds a dominant lead at 29%, which nearly doubles the market share of Europe or North America. The text emphasizes that BRICS nations are leveraging their massive user bases. We're talking over 4 billion users and heavily expanding their domestic fabrication facilities. By pursuing these next-generation quantum photonic, AI chips, they're effectively bypassing the traditional silicon bottlenecks and the highly restricted EUV lithography machines that currently dominate the traditional semiconductor industry altogether. The author details some really incredible architectural breakthroughs happening right now in Chinese universities and startups. For instance, the Taichi chiplet is hitting massive energy efficiency at 160 tera operations per second per watt. Meanwhile, tri-stable crystals are allowing light to hold 3 stable states, breaking right past standard binary. Add in domestic pilot lines for 6-inch optical wafers in cities like Wuxi, and we are seeing complex neural systems execute completely within the optical domain. Let's move to and see how this builds into our final takeaway. Section 4. A light-speed future. Seeing beyond the silicon fog. Ultimately, the source concludes that photonic processing successfully overcomes the severe heat, analog, and power limitations that AI pioneers like Geoffrey Hinton and Fei-Fei Li have long warned us about. By utilizing photons, we are clearing away the fog of electron-based computing limits, stepping onto a brightly lit pathway toward a sustainable, high-speed, and ultra-low-energy cyber-intelligence future. Which leaves us with his final provocative thought to ponder. As we reach the physical limits of traditional silicon, the global race for AI dominance is fundamentally shifting. Based on everything we've explored today in Dr. Lakeman's text, will the future of artificial intelligence be won by those who master light rather than those who master electricity? Thanks for joining me on this explainer, and keep questioning the technology that shapes our world.